Right, welcome everybody. This is obviously you can see that I've dedicated my talk to Barry Keane and Bob Samuel and Bob Grief. Obviously, sort of three members of the society who passed away recently. Barry was a fellow of the Royal Astronomical Society and keen solar observer. I met his son and got some of his notes a few weekends ago, and a few other bits and bobs, including a really, really great plates or really old slides, or one which we'll see an image of later in the talk. Bob Samuel, obviously a great astrophotographer and lived very far away, but still managed to get to most of our meetings. And Bob Grief, who's a really passionate educator in many things, including astronomy. So this is dedicated to those fine members or former members of our society. So this actually begins with this book. It's a book I picked up at Oxfam in October, and it's very good. I got three of them at £6 each, and I thought, in Oxfam, I was dropping some stuff off, and I thought, let's sort of like, have a look at these books. They really sort of looked quite interesting and stuff. And I sort of then scrolled through them, and they are from the 1890s. Obviously making them exceptionally old, and they're in exceptionally good condition as well. A couple of pages are becoming loose, but considering they're about 130 years old ish, they were in great shape. So I sort of spent time reading them, and as you'd expect me to do, I would focus on the astronomical parts of it, but I will go through a little bit of the more amusing sections of this book before we get into the talk. It was rather bizarre hodgepodge of subjects which were covered. One book has sequential chapters which included the anatomy of a lobster, rust, a glass of wine, and voyages in cloudland. And these were the pictures of flying machines which people attempted to use from that book. Obviously, it was pre-Wright brothers. And you've got a couple of guys there who have been literally lobbed out of a balloon and then sort of like try to pedal themselves into some sort of powered flight, but inevitably didn't make it. And Mr. de Groot on the left and Mr. Latour on the right, unfortunately fell to a demise after that. But in essence, de Groot and Latour's flying machines were victim to the fundamental problem. That is the theory of Vulcan's existence, which is gravity. But we'll go more into that detail later on. Other things that didn't appear into the book was X-rays, which was discovered in 1895 by William Roentgen. Radioactivity, sort of joint discovered by Henry Becquerel and Madame Curie, and things like the Nobel gases, with the exception, of 1898. So that's neon, argon, krypton, and xenon. They were not even in this book. So that just shows you the age of these books themselves. But certain things which were in the book, which were very interesting, were things like the harmony of the moons. So I'll read a little chapter from one of the books here. The discovery of two satellites attendant on Mars adds another link to the harmony of the solar system. For so far as our telescopes are capable of revealing, the number of the moons furnished to the planets, I love that word, furnished to the planets, increased accordingly with their distances from the sun. Thus, the Earth has one satellite, Mars has two, which are obviously Phobos and Deimos, Jupiter 4, and Saturn had 8 discovered satellites in this book. And they then sort of went on to surmise that Uranus would have 16 and Neptune would have 32 satellites, because they thought that basically as you moved further out of the solar system, the number of satellites would double from 1 to 2 to 4. Obviously, that wasn't the case, but that's the sort of the other part of this talk, which, sort of associated with Vulcan, is maths and mathematics and those sort of things there. I'm just going to have a quick talk about the Titius-Bode law, and it is where the sort of the planets existed according to a mathematical equation. Some of you may have seen this before. The table there shows a Titius-Bode law, the mathematical distance from the equation, which isn't really that complicated, and the actual astronomical units where the planets are. And you can probably see that, the astronomical units were pretty right. So this mathematical model that was used was sort of, pretty close to the mark there. And going through one of the other books, when this paper was published, Johannes Kepler wrote an introduction to one of Professor Titius's work, and he says he has become bolder and now placed a new planet between Jupiter and Mars, obviously represented as the asteroid belt as we know now, as well as another between Venus and Mercury, probably an extreme smallness of both, which has caused them to remain unseen. Now, this was Johannes Kepler talking in around about that time, and he sort of, this obviously the Bode law was a lot earlier than the book's publication, but he thought that there was another planet out there between Venus and Mercury, and we teach Kepler's law at A-level physics, so we're talking about one of sort of the big guys of science. And so before we take our journey through the solar system, for those who might not sort of have much of a physics or astronomical background, just do a little bit of about the discovery of the other planets. So Uranus, first planet to be discovered after Newton had formulated his universal law of gravitation there, on the 13th of March 1781 by William Herschel. And that was 95 years between the discovery of Uranus and Newton's published books, Principia Mathematica. But that discovery was quite important because it allowed the sort of first observations of Uranus, and it allowed the equation, which was quite famous from Newton, to be put through its paces, as it were. And that was done by Pierre Simon Laplace. He took Newton's equation and he started sort of employing them to Uranus's orbit. And just give you a bit of an idea of the equation itself. That's the equation that the mass of two objects, the gravity or the attraction between the two objects, the force between them is dependent on the mass of one object, the mass of the other object, and the radius between the two, over the radius of the squared between the two, and multiplied by the gravitational constant. So this caused a bit of an issue at the time, because Jupiter and Saturn didn't behave to this law, and they kept sort of being at different places where they were expected prior to the discovery of Uranus. So, discovery of Uranus was important to them, and they had to sort of use Uranus to maybe use it as a third body in sort of the Jupiter and Saturn sort of system, to sort of work out why Jupiter was moving probably a bit too fast and Saturn was a bit too slow. So they had to sort of take not just two bodies, as the equation states there, but they had to sort of take multiple bodies of the solar system, which is obviously a lot more complex. And I didn't even look at that equation. But so Uranus was sort of influencing Jupiter and Saturn at the time. And Pierre Simon Laplace was unhappy with the Jupiter-Saturn issue, so he took 3 years of working on it. The book calls him an analytical grunt, so there's a lot of analytical grunt work done, completed. And in 1788, he concluded there was minor gravitational variations between Jupiter and Saturn. So they were influencing each other, and Uranus was sort of influencing them as well. And with that information, Pierre Simon Laplace came up with the celestial mechanics, basically, which was 1,500 words, 5 volumes of dense equations and analysis, and this was the birth of celestial mechanics. And when Mr. Simon Laplace met Napoleon Bonaparte, Napoleon asked why wasn't sort of God in these equations? And to that, Napoleon or his Simon Laplace says, "Your Highness, I have no need of this hypothesis." So that was quite a nice sort of retort to old Napoleon Bonaparte. Quite brave, I'm sure. But yeah, we would have to bring in yeah. So that was basically how it's left for a long time. There was sort of 7 years between the planet's discovery and between 7 years between the planet's discovery, Uranus, and Pierre-Simon Laplace's new celestial mechanics. And that was quite difficult because 7 years, Uranus doesn't move that much. So observational data is quite limited, but he was able to use what data they had. And that would be the sort of the end of it's the beginning of celestial mechanics, and Pierre-Simon Laplace has created it. We moved on to the uranium problem. And this is basically this entire talk revolves around Leverrier, who was I think he was a tobacconist whale or something like that before he became a chemist at the Paris University, and then he sort of got involved in doing sort of hard maths and looking at observational data and making it better and various things like that. And with the data that was accumulated, Leverrier sort of took Simon Laplace's celestial mechanics and all the information that he had acquired, and he made it better. He sort of refined it, and he made the information sort of like a bit, put extra sort of equations in, and sort of like just really sort of tidied up what was going on there. And he would he worked on the four inner planets as we know them to be Mercury, Venus, Earth, and Mars, and he really sort of like provided a much higher mathematical resolution of their motion through the solar system. And he took celestial mechanics and the idea that he could predict the future orbit of planets. And that was a really, really sort of big thing to say that, celestial mechanics can then predict where planets should be in their future. And he was, he'd done in 2 years of joining as an assistant at the Parisian Observatory University, and as a chemist, assistant to the chemistry department. In 2 years, he had he'd basically sort of come up with these things and basically said that you could predict the future with celestial mechanics, and he was right. And in 2 years, that was a sort of a big thing. And he started sort of like, thinking about Uranus and sort of like, because it was sort of misbehaving as well in its orbit. Pierre-Simon Laplace had looked at Jupiter and Saturn and worked out Uranus was mainly the problem there. But then, Uranus was also being sort of moved around in an unnatural way. And that's an unnatural way according to Newton's equations and stuff. But he sort of didn't look at Uranus at the time. He'd actually looked at Mercury, and he started having a look at why Mercury was misbehaving as well. So by this time, there's sort of lots of sort of discrepancies between this sort of the future that celestial mechanics could predict, in terms of the fact that that Mercury was not being where it should be, and Uranus was not being where it should be, and various other things like that. And from 1836 to 1842, he had 200 observations of Mercury carried out by various astronomers, so he could get his mathematical data. And he did a sort of slight adjustments to various things like the astronomical unit and Mercury's mass and stuff. But Mercury was still misbehaving. It was still being, it had what was called advancement of the perihelion. So when Mercury is closest to the sun, it would be where, it sort of almost sped up, or sort of like, or went on a slightly different orbit, which we'll talk about later. And it was there was basically people waiting for a transit of Mercury, and that was the best thing that they could do with astronomical equipment at the time. And in 1845 there was a transit of Mercury, and so they timed it as best they possibly could. and there was a 16-second difference between Mercury moving across the sun's disk, as you can see there, not that in a transit, and the equations that Leverrier had used to predict where Mercury should be. 16 seconds is a bit of a it was 16 seconds late, so that's a big difference. There was obviously something really fundamentally wrong going on there, and Leverrier would be, sort of like trying to work out what part of the equation that he had in front of him, massive equations, I assume, which wasn't actually working there. But unfortunately, his boss said that they had a much larger problem, and that would be the problem of Uranus. So Leverrier's boss at the university said, ignore Mercury for now, we don't care about that, there's a bigger problem with Uranus. And so they are looking at that. Now, Laplace's students, Alexis Bouvard, pictured there, he already attempted to use celestial mechanics for the Uranian orbit, and observed the planet for a long, long time. Eugene Bouvard, couldn't find a photo of him, who's Alexis Bouvard's nephew, then moved on to say that his uncle secretly thought that there was an anomaly out in space that sort of perturbed the Uranian orbit. And he was quoted saying, it's entirely implausible that the idea suggested by my uncle is another planet perturbing Uranus. But Alexis Bouvard wasn't brave enough to sort of come out and say that directly. He sort of kept it to sort of, his closest confidants and his family. But eventually his nephew Eugene, turned up and said, he took his uncle's work forward and said that there was probably something out there sort of just, disturbing the Uranian orbit. And various ideas started getting thrown around. There was this very strange idea, which do appear in the books, that there was some sort of like drag in space, that space itself wasn't empty, and that it was full of some sort of ether, which Leverrier originally thought, that's not, that can't be it, because it'd be affecting other planets and stuff like that. They thought that there was a giant moon around Uranus, sort of pulling on it and sort of like pulling it around and stuff. But you'd thought that they would probably be able to see that even with the telescopes at the time. So Leverrier decided that that wasn't the case. Oddly, they thought there was a sort of galactic collision, like something like a comet, and that hit Uranus and sort of slowed it down. Now, probably that did happen because the tilt of Uranus is 90 degrees ish, so that could have happened. But still, out of the four theories, Leverrier was unhappy with these three, and so he sort of conceded that there was possibly something out there, and he started writing down his equations to sort of try and find out what could possibly be out there. Now, originally he came up with 13 unknown variables in an equation, which is absolutely just a staggering number of variables if you don't know what those numbers are. And he actually sort of managed to sort of do the bit of jiggery pokery on the arithmetic, take it down to 9 variables of the unknown. And being the sort of man he was, having read on him for the past sort of 6 to 8 months, he definitely came across from research to be the man who would sit there and muck around with 9 variables that he wasn't fully interested or didn't fully know. And so he said it was a very not impossible to calculation, but a very difficult one. So he'd worked out that the perturber of Uranus was at 36 astronomical units away, oddly 36 times the mass of the Earth, which is a sort of an odds coincidence as well. And it was located in Capricorn somewhere. And in 1846 came around, and by the 31st of August 1846, he had determined that there was this object would be about 5 degrees from Delta Capricorn. So this is Deneb Al-Jedi, Al-Jidi, and that sort of like star at the top there. And he said that was in 5 degrees of that, roughly. And so Mr. Leverrier took it to his sort of French compatriots, and they did absolutely nothing with it at all. Nothing at all. They didn't even bother looking in that region of the sky with any of their astronomical instruments. Various sort of political things are happening along in the observatory and the university and stuff. So, as you can imagine, Leverrier had spent all his time trying to work out where this place was. And he'd lost patience by the 18th of September in about 3 weeks' time, and he phoned his friend Gottfried Gale in Berlin, and on the 23rd of September 1846, Neptune was discovered, as you can see at the top there. Deneb Al Jedi is down the bottom there, and it's quite interesting to think how close was his calculations, bearing in mind he thought it would be within 5 degrees roughly of that prediction. And with the magical stellarium, you can chuck in one of these, and he got it to 4 degrees 56 minutes for 16 seconds. So that's pretty good, considering he was doing all this by hand and all the calculations by hand. He'd done pretty well there, I think, and that's very impressive indeed. And so it was actually the sort of Berlin Observatory that got the accolades of discovering Neptune. So really, it was Gottfried Gale who discovered Neptune, and Leverrier discovered the existence of Neptune. I think it's probably the best thing to say. So he's obviously attributed to sort of discovering Neptune, but he discovered where it should be. And yeah, Neptune was there. Now, it's there is a bit of a discrepancy here, which I found during the research. I had several books that I was reading to research this, and one of them was a recent one done by Thomas Levinson, and he stated that the planet Neptune would be 21 hours, 53 minutes, and 25 seconds of right ascension. You can see on there that second number in next to the -13. That 21 hours, 53 minutes, and 25 seconds is pretty close to what he had there. And in their book, Sheen and Brown, which is a bit older, stated that that Neptune was about 13 degrees and 24 minutes on its declination. So both the books got it right. And that was where, this is from Berlin, this is Stellarium, using all the times and the dates, and that was pretty good. Now, the thing I did discover, just to give you an idea, if you don't know Stellarium too well, is if you sort of take a line and you move it from, say, south, or from the horizon to above your head, that's 90 degrees. If you go from the horizon above your head to behind you, that's 180 degrees. The reason why I'm telling you this is because on the Wikipedia page, the discovery of Neptune states that it's within 1 degree of Phi Aquarii. And I thought, well, hang on. It's like this book said it was in Capricorn. So where on earth is it, in relation to Phi Aquarii? So I thought, well, maybe it's quite close by. It really isn't that close by. Phi Aquarii is actually 19 degrees, a lot further away than the Wikipedia page states. And so I thought, well, maybe they've got it wrong. Maybe it's within 1 degree of somewhere else. It's actually 1 degree distant from Iota Aquarii. So I actually possibly think, unless there's something I'm completely missing here, that Wikipedia has got this wrong, and whoever's put it up there, it is wrong. And you think, the discovery of Neptune would be a pretty big scientific achievement, or a pretty big scientific sort of discovery, and they've actually got it wrong on Wikipedia. So, but maybe they haven't. Maybe they've done something like renamed the stars, or maybe it was sort of misinterpreted from sort of the sources or something like that. But that's sort of something to be looked into a bit further later. So, discovering planets was originally sort of obviously through observation, but now mathematics has sort of trumped it. We've found all the planets, with Uranus being the last one to be observed directly and discovered. Mathematics then has started predicted where planets and other planets were discovered using that, or basically one other planet had been discovered using that, which is Neptune. And so that he was obviously hugely celebrated. And old Leverrier went back to his Mercury problem. So he went all the way back to Mercury, which he wanted to do in the first place before he was taken away. And you know, he had some justification here. He had some brilliant, you know, results using his new mathematical equations derived from celestial mechanics and stuff. And he started sort of like to look at Mercury's orbit. Now it was perturbed by 565 arc seconds per century. So basically, it means the entire orbit is perturbed. So not just Mercury itself, the entire orbit is being shifted around. And so that was the sort of disturbing thing for Leverrier. And he came up with all sorts of things that he sort of like managed to work out. And he came to a that even Uranus was sort of disrupting Mercury's orbit, even as being so far away. Sort of the biggest sort of culprits of Jupiter and Venus. But he had a variance as he sort of added them all up of 38 arc seconds per century that could not be accounted for. Now we have to remember here that the only sort of like real celestial mechanics which were sort of used at the time were sort of things like, you know, which Newton had been using and, you know, discovered, and variations of Newton's framework was used, and that's what Leverrier employed. But it's he basically sort of couldn't work out why there was a 38 second per century arc second per century variance. And he says Leverrier has felt justified that Newton mechanics could resolve it, and he stated, these days the principle has acquired such a degree of certainty that we will not allow it to be altered. So he was such a big student and a big champion of Newton mechanics, he would not even dream of trying to do something else. It says, in the tables of the motion of Mercury, do not strictly agree with the group of observations, will certainly not be tempted in changing the law of the universal gravitations with inadequacy. So he's basically got all his eggs in a Newtonian basket. And he would not be sort of dissuaded in any way, not that anyone was trying, that Newton's equations weren't sort of up for the task here. And so the only thing that he could say is, once there was sort of with Uranus, there was sort of this variance in the Uranian orbit, there's a variance in the orbit of Mercury. He had to sort of like come up with, it assumed that there was another planet. It would only be possible that there was another planet between Mercury and the Sun. And that was the birth. That was sort of this, well, the birth of the idea of this new planet. And so it came to sort of a French doctor in France, and this is his observatory, who had been observing, you know, the sun. He was a keen solar observer, and he had been observing the sun between patients, pretty much, you know, for many sort of like months, if not years. And he had a sort of a 3.7-inch refractor. And March 1859, he recorded something moving across the sun's disk that was not a sunspot. And it took 1 hour, 17 minutes, and 9 seconds to traverse the portion of the disk it was going across. And he basically sort of then wrote to Leverrier and said, I've seen something move across the sun's disk. So Leverrier went like hurtling down from Paris to Algiers, and basically sort of just to sort of check, you know, so interview Mr. Lescarbot, and sort of just to sort of see what sort of setup he had. And Leverrier was quite impressed with the telescope and sign. He was a bit disturbed, but the fact that the clock that Lescarbot was using to time things didn't have a seconds hand. And he was completely sort of thinking, well, this guy must be some sort of clown, you know, how can you time the seconds of a transit without a second hand on the clock? And Lescarbot, being a sort of a physician, a general practitioner, he said that he was, you know, completely, you know, he felt that he was good enough to kind of sort of a certain number of seconds when he's taking patients' pulses. So he said he didn't need that second hand on a clock. And he was a very accurate solar observer. And they sort of had a sort of a good old meeting, and Leverrier was convinced. And this is what was seen by Lescarbot. There's no actual images or drawings of what he saw, but this is a rough idea from one of the books. That was the transit that allegedly Lescarbot had seen or observed. Now, That's like not like a proper transit like we saw before, where it goes across the disk of the sun from one side to the other. It's brilliant. This was a very sort of a grazing transit, and it was, could you be completely sure that that was a new planet moving across the sun? Anyway, Leverrier was so keen that he this planet was born, and he said, "Well, we're gonna name this planet, and what better name to give the planet was Venus's husband, Lord of the Forge, Vulcan, and that term was coined around February 1860. So Vulcan is officially considered to be a planet. Now you need to get some more observations of this. But first, before then, we're going to go back to one of the books. So this is one of the images I scanned from the book, and this is really where the whole talk came from. Was this sort of model of, or this diagram of the solar system in the book? Talk about the author of these, all the astronomy articles in that book later. But I noticed that the diagram, if you can see it written at the bottom there, relative positions of the orbit of Vulcan and Mercury. So I thought, wow, that'd be good, isn't it? So if Earth is like 10.55 centimeters away from the sun on that diagram, you can sort of like extrapolate backwards. And it turns out to be that Vulcan, according to this, was about sort of 0.11 astronomical units away from the sun, which is about average orbital distance of about 16 million kilometers or something along those lines. And now the race was on to get more Vulcan observations and stuff. So there we have Lescarval in France, March in 1859. He discovered it. He sat on it for 9 months, and he didn't sort of like tell Leverrier until later on. At exactly the same time, another Monsieur Liaeus in Brazil at the same time was observing the sun exactly the same time as Lescarval, and he did not see it. So there's sort of obviously the first sort of discrepancy there. There are Mr. Capel Loft. It's a great name, isn't it? I don't know if Capel is spelled there. Of Ipswich, of all places, observed the Vulcan on January 1818. So he'd gone through his notes back to January 1818. He said, "Yeah, I've seen Vulcan. I've seen it through a reflector and a refractor." Then Mr. Freach, I'm not sure of the location, said he's seen it twice in 1800 from his notes, March and October there. There was also Mr. Wilson, who had allegedly seen it on August 1858. And there was a Mr. Loomis or Lummis. He saw around 8 a.m. during March 1862. This stage is interesting to note about transits. So the transit of Mercury always occurs on May or November. Not all the time, but it's always 6 months between the 2 months, May or November, and that was it. November of last year, there was the last transit. There's not going to be another one until 2032. Transit of Venus occurs in pairs, but those pairs are either in June or December. So the last pair of transits were June 2004 and June 2012. The next pair of transits will be December 2117 and December 2125. So there's 6 months between transits. There's some sort of 6 months variation between the planet transits. As you can see with the Vulcan observed section, the months are a little bit all over the shop. There's definitely not one month, oh yeah, we all saw it that month and then we didn't see it for another 6 months. They are all over the place there. So that led me to believe, well, maybe they're not seeing it at all. Mr. Cumbre in Turkey saw it in 1685 for 48 minutes, allegedly. There he is. There was just apparently 4 expert solar observers, and one of them claimed to see it with the naked eye from Iowa in 1869, which is like they concluded what they saw with the naked eye to be Vulcan. I mean, that's just crazy that you'd see it there. One of the more sort of odd ones was this image from a Captain Herschel in India in October 1869. He said, well, maybe it's not a planet. Maybe I've drawn these images here, and maybe it's asteroids. Maybe there's an asteroid belt between it. Volcanoids. and maybe that's what's sort of like sort of the sort of the issue with Mercury in orbit, that was so small that there is a volcanoid asteroid belt, and that was you couldn't see it. And Leverrier was actually a bit more of a fan of this rather than the sort of the planet himself, and he drew these images here, and that really doesn't look like anything you'd usually see on the sun. But he said that the right hand image flew away, and it was confirmed that in India at the time, a swarm of locusts descended on the sort of the country, and what he was seeing through his telescopes was swarms of locusts between him and the sun. So, and you can probably think, yeah, well, that's probably like a swarm of locusts there. Um, Other people who hadn't seen it was somebody called Hofrath Schwabe of Dessau, and he'd every opportunity observed the sun every day for 40 years, and he had not recorded anything moving across the sun's disk in that time, which is a big, sort of like no, for not observing this planet. But if you see there's lots of people who said they had seen it. But there was sort of people who hadn't seen it. The transit method wasn't really working anywhere else. So the current score between Vulcanists and Vulcan pessimists is 1-0. People said, well, let's use an eclipse. Let's get out that find eclipse. Solar photography was quite at its sort of infancy at the time, and so the man who got the first PhD in astronomy ever, Benjamin Gould, decided that sort of using a solar eclipse to see Vulcan would be the best thing. And 1889 solar eclipse plate here was one which was left to the observatory by Barry Keenan. So actually, it's a physical plate from the British Astronomical Association. That just, it's amazing to hold something from 1889. So yeah, that's just thought I'd shove a picture of that in there. But he'd sort of Benjamin Gould had studied maths and quite a PhD in astronomy in 1848, so he was obviously a very educated man, and he sort of like started thinking about using the solar eclipse method. But the guy who wrote a majority of articles in the Science for books, he started getting people together to try and find this item and stuff like that, this planet. And so, but before then, Mr. Weber, Henrik Weber, was a well-trained professional astronomer, said that in 1876 he saw Vulcan crossing the disk of the sun. And you can see that's just thrown another month amongst the sort of amongst the lot there, and that is, that's just, you nearly got all the months there. But William F. Denning, who was the writer of these, in 1869 he persuaded 15 other astronomers to sort of go hunting for Vulcan between March and April in 1869, and found nothing. He then, in 1870 and 1871, managed to get 25 astronomers all together and sort of corresponding with them and all that. And in those 2 years, he still didn't see Vulcan at all. So he really was sort of pressing hard to try and observe Vulcan. Here's the article from the book, which is where this originates, Science for All, A Supposed New Planet by William Denning, there. And he was, a fellow of the Royal Astronomical Society. And you'd thought that by this point, he would be thinking along the lines of, okay, well, it's not there. It's the planet's not there at all. But he didn't even believe that after all that search for 3 years. He suggested that maybe the astronomical equipment wasn't up to the task at the time. Maybe something along the lines that Vulcan's orbit was too inclined to the ecliptic plane, so it was moving too far above or below the sun, so transits were very rare, and various things like that. So even though he sort of never saw it and put so much of his time to see this planet, he never actually even convinced himself that it wasn't there. But that's a bit more going on the right hand side there. So that is now, the score is now Vulcanists 1, Vulcan pessimists 1. So there's sort of the balanced score there. something had to be done. I mean, Vulcan was sort of proven to be a bit of a problem. You know, it still had that 38 arc-second per century issue there. So the big heavyweights came in for the next solar eclipse. And they, one of them was Thomas Edison. Obviously, doesn't need an introduction. He sort of jumped into this foray. Henry Draper, sort of one of the pioneers of astrophotography of that era, and sort of astronomer as well. Founder of Nature and Spectroscopy, Norman Lockyer, he got involved as well, and director of the Ann Arbor Observatory, James Watson, got involved. So, and loads of other people jumped in to see this big solar eclipse that was going to occur in 1878. And there's a couple of them there. There's Edison on the right-hand side, just off the right, and there is Watson there. You can see that they've got their equipment, and they're sort of ready to, they descended on Rawlins in Wyoming for the 1878 solar eclipse. And you thought, well, here we go. These are the big guns. These have got the best equipment. These are well-off guys, you know, people like Edison. They've got good equipment. They've got some good knowledge. You know, a lot of sort of mathematicians there, a lot of really good knowledge. They weren't the only group to go to Rawlins in that time, and there was other groups, which include sort of other people and other scientists. And you thought, would Vulcan stand up to the scrutiny of these scientific giants? I mean, surely these guys who are sort of renowned scientists would not see Vulcan. Here is Craig Watson's drawing, an actual scan of his original drawing in 1878. There's the ecliptic plane, where the sun would be. There's a few stars knocking around there, and you think, you know, he's a man. He should be knowing what's going on there. But if we look just in that little red circle there on James Watson's note, he says, "There's Vulcan, 1878 on July the 29th, July 29." And yeah, he actually said, "Yeah, I saw Vulcan. That's great." And so it was like, oh no, even the sort of Vulcan as being sort of Vulcan mania has sort of got into the scientific community as well. The sort of the real big sort of heavy hitters of astronomy. Apparently, he had seen it. And to give you a bit of an idea where it was, this is the total solar eclipse there. That's Delta Cancri, M44, which was on Watson's diagram there. Theta Cancri, and Vulcan should appear to roughly about there, according to his map. And you know, that was it. Vulcan was definitely there. You know, it had been seen by the professionals. And the New York Times wrote that one brilliant discovery will probably date from this occasion, that day. The planet Vulcan, after so long eluding the hunters, showing them from time to time only uncertain traces and signs, appears to have at last been fair, run down, and captured. And that was the New York Times. So they'd sort of kind of run with it. The Times in the UK printed negative results of Professors Newcomb, Wheeler, Holden, who were in a different party, who with similar instruments went over the same ground and found nothing, are indeed unsatisfactory and puzzling. So on one hand, you've got like the Americans going, "It's been fine, Vulcan, yeah," and you've got the sort of the Times saying, "Yeah, well, we pretty much think you didn't sort of find this item, this planet and stuff." So Vulcan was discovered, but it was always a bit of an enigma. You know, it was sort of Vulcan was only to be found when it was sought in the faith that it had to exist, but never anyone tried to confirm or was persuaded by somebody else. So basically, it's sort of kind of like Schrodinger's planet, that as long as you didn't look for it, it was there, but as soon as you tried to look for it, it disappeared. So it's there was sort of, it had a potential existence through maths, but actually nobody had seen it. So that would sort of like be where it sat for a long time. And yeah, it was proven to exist by celestial mechanics and Newton's equations and Leverrier. It had now been seen by professional astronomers and amateur astronomers. And, you know, that would sort of like, you know, that would be the way it is. But from then on, people stopped talking about Vulcan from about its sort of discovery, or it was the naming of it in 1860. People sort of like didn't really want to talk about it too much. And there's very little information about Vulcan from 1860 onwards. So Vulcan got sort of like denominated to sort of like, that was Vulcanists 1 and Vulcan Pessimist 1, so very even there. But Vulcan got denominated to be the mad uncle who lived in the attic And nobody really sort of bothered with it until sort of a young man from Switzerland turned up much later, who was sort of thinking of something completely different. And he was looking at for instance, him, I think we all recognise him there, Albert Einstein in his younger days. He'd already sort of come up with special relativity. And special relativity, which came before general relativity, was sort of involved basically in a nutshell. It was called special because it occurs in flat space time, which is sort of Euclidean space. So space is flat. And events in there, so people would see like events differently from other people, so depending on their existence. So in a classical thought experiment by Einstein, here you see train moving from right to left, two lightning strikes at the edge of the platform there. The train keeps on moving. The guy on the platform sort of sits there, but the guy on the train sees one lightning strike before the other. And the guy on the platform on the bottom sees a lightning strike at the same time. But did the lightning strike hit in the same point in the past? And sort of things like that, which it did, but it really depends on how fast you are moving, and which of the sort of light waves would actually get to you first. And so that was a sort of a rough idea of special relativity. So he'd come up with the idea that space and time were the same things, but that was in Euclidean geometry, so flat space time. And so he sort of, as he was thinking, this is, many people think this is the window cleaner falling off his ladder or off the roof experiment. But he came up with this idea, sort of getting a bit further on, around about sort of 1910 or something like that, that there's a man and he's in a box, and attached to the box is a rope, and he's floating around in space. He can't see anything outside the box. And somebody pulls on the rope, and of course the man will sort of, like, his feet would touch the bottom of the box there, but he doesn't know what's going on outside. But in the same instance, you have the Earth, and you have the same man in the box, and the Earth is obviously going to pull them down. So as long as you pull the box with the force of 1g, the box would sort of, like, the man in the box would feel 1g of force, but he couldn't tell if he's being accelerated at 1g or if he's been, experienced gravity at 1g. So he started thinking that, in a nutshell, gravity and acceleration are roughly the same sort of thing, that they both warp space and time, and this is where general relativity came in. So apologies for the sort of the clarity of these images here. I couldn't find a large version of it. Yeah, there you have the Earth in Newton's fixed space, and there you have Einstein's flexible space-time, so the Earth causing a dent in space and time. And Newton obviously thought that gravity was completely different from space, from time and space, that it didn't have like any connection at all. But to say his equations is awful isn't right, because obviously you can still fire a cannonball and Newton's laws will sort of govern. You can work out various things about it and land a man on the moon and get probes to Mars and various things. It's sort of like, whereas Newton's equation, it's best to think of Newton's equation as like a low resolution image of sort of space and time, and Einstein's is a bit more sort of like, accurate, a bit more high definition, I think is the best way. And yeah, the sort of Einstein came up with this flexible space-time, and sort of various orbits being sort of like moving around in this start misbehaving, and this is what was trying to be resolved here, that Mercury's perihelion was its closest approach to the sun was being shifted, and therefore the entire orbit was being shifted as well. And I've got a little a bit of an animation here to give you a bit more of an idea of what that looks like. This is actually not using Mercury, but using a star going around Sagittarius A star. So we can see here, that Mercury is moving around, or Mercury should be moving around the sun, but this is moving around the black hole, and you can see a bit more of an animation of what's going on here. So as the star in this instance is moving closer to the black hole, you can see its orbit is being changed each time, and it's eventually going to form a rosette. Quite like that. That's quite a pretty animation there. But I'm not quite worked out why the black hole flashes each time the planet goes close to it. But that's a nice sort of animation there to give you a bit more of an idea of what was going on. So this is where it sort of diverges a little bit. So you got Euclidean space, which is flat, and then you got non-Euclidean spaces now being formed from the sun and various things being sort of put into that flat things and warping it. And non-Euclidean space includes things like cylinders as non-Euclidean, spheres, Pringles crisps, all those sort of things. And so Mercury's orbit is attempting to move in sort of like through this sort of deep gravity well, and its sort of shortest path it can take has to mean that its perihelion moves so it can sort of like continue its orbit according to non-Euclidean space. Now, which was the really big equation that Einstein used? So he used this equation on the 18th of November 1915. Here it is. This is, I should really get a picture of like the Death Star or something blowing up Alderaan, but this was the planet destroying equation here, where you've got the whatever that symbol is there in radians per revolution. L is the semi-major axis. T is time, usually in seconds. C is obviously the speed of light. E is the eccentricity of the orbit of the planet. And you can see that really, well, where's gravity? Where I just spent all this time talking about gravity. Gravity is, where is it involved? Where is it in this equation? Well, it's actually this equation comes from a lot of other variations in the theory of general relativity. So general transformation of coordinates using 4 coordinates, and the fourth one being time. Gravitational field of a particle, how it behaves. Einstein's law on gravitation. And equations on geodesic path between 2 points. Now, I'm not going to bamboozle you with all those equations because they're a bit heavy. But the gravity is incorporated in an equation that is this equation is a derivative of. And he plugged these sort of numbers in, and he came out with sort of numbers like this. So as I mentioned, it was 16 arc seconds, but it was that was sort of the first attempt. It actually came out to be 43 arc seconds, which Mercury's orbit was perturbed by, and the equations that came up here from Einstein is he did all right. That was pretty good, and this was the first real test of general relativity here, and that was a great result for him. Other tests came along, and there's sort of like the test of sort of starlight moving through eclipses and sort of gravitational waves. But this was the first real test, and I think he was quietly pleased that he'd solved the Mercury problem. And it was a complete resolution. So at that time, really, in 1915, there was no need for Vulcan anymore. We'd found a brand new framework in the theory of relativity that explained why Mercury was misbehaving, and that was sort of like, it wasn't anything to do with Newton's equations. It just wasn't sort of the right equation to sort of resolve the problem there. And there was sort of various other things that everybody started using this equation. And in the red box here, Mercury is moving around, and various things like Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune even, and the blatantness of the sun all sort of added up here to sort of like cause this motion of the perihelion. And actually these numbers are a little bit different because they've got a general precession there. So I've sort of thrown in an extra the number there. So generally what was seen is sort of 531 arc seconds per century is calculated. And the relativity effect at the bottom there accounts for 43 arc seconds there. And then you got the Earth as well. The Earth has its perihelion is perturbed, but we have a much more circular orbit, so we don't really see that effect. So that's why we're only sort of 4.6 arc seconds down in the bottom right of that first image. When Mercury Messenger space probe went there with all its technology, it even then started calculating mad things like the asteroids having an effect on Mercury's orbit, various interactions between sort of different planets and the moon, and all sorts of stuff was sort of thrown in there, but coming and to sort of give you a much higher resolution of what on earth was going on. And gravitoelectric down at the bottom there is now sort of substituted as the relativity effect. And then you get really crazy things like gravitomagnetic effects as well. So sort of best sort of to describe what's happening here. So if you sort of kind of imagine you've got all these planets sort of whizzing around the sun, they're all warping space-time, they're all affecting each other, and they're all sort of like, you know, moving each other's perihelion around if they're getting like, you know, all one side, and there's various things. We don't see it so much because we're on a very circular orbit. So Mercury's one of the most elliptical orbits, so that's why we can see it more on Mercury there. So where's Vulcan left us for now? You know, where is it left the sort of the solar system now that we don't need a Vulcan anymore? We you know, we might sort of think that you know, there's a Planet 9. It's a big thing in astronomy at the moment. I'm not sure about unspeakable horrors and paralyzing and the living and resurrecting the dead, paralyze the living and resurrecting the dead, but you never know. Planet 9 from outer space might involve this. The sort of legacy of Vulcan, when we met Chris Lintott, like last year in the middle there, at British Science Festival, I asked this question to him. I asked him about specifically this picture, because I've seen it before. That Planet 9, where is Planet 9 a planet that exists? And does that, you know, is it waiting out there in the depths of the solar system? And he said yes. He said yes, it does exist. I mean, he's pretty much saying that the maths suggests that it's there. And so we are, you know, it's got to be there. You know, there's all these orbits of the sednoids, you know, on the left-hand side there, and nothing on the right-hand side. These are very, very far away. I mean, the orbit of Sedna is 8.6 billion miles, which is 5.4 light days when it gets its furthest away from the sun. So, you know, all these things are on the left-hand side. There's nothing really on the right-hand side. Alan Stern of the New Horizons team, who took obviously the image of Pluto, gets a bit hot under the collar about this Planet 9 business. He reckons it should be called Planet 10 because Planet 9's already taken. And, you know, in his mind, Pluto is still Planet 9. Whatever the planet's called, it can't be called Vulcan because the International Astronomy Union has already reserved this name, you know, just in case like it might actually be out there. But what candidates are there for Planet 9? I mean, does it actually exist out there? Planet 9 could include, well, Nemesis, the Sun's brown dwarf companion, was from 1984. Was a hypothetical red dwarf star, which was a companion, or brown dwarf star. And it was sort of disproved by the Wide Field Infrared Survey mission because they didn't find anything lurking around out there which could be a companion star. Taish, which was, I suppose, another gas giant out in the solar system, was also disproved to exist by the same mission. Something called Gna, which is a fast-moving planet, 12 to 25 AU, and about 220 to 880 kilometers in diameter, very precise. That's sort of another theory for Planet 9 there. Brown's Planet 9. He says that there's a 0.2, so this is it's Mike Brown from Caltech, says there's a 0.2% probability that there is not a Planet 9 out there. And basically, it would be probably around 21st to 24th magnitude. And yeah, so Brown's Planet 9 suggests that there is, it's out there. It's about 6 Earth masses and has a period about 10 to 20,000 years. And the reason to say that he thinks that it hasn't been discovered is because there's not enough orbital data for other planets at the minute. I mean, you know, that's sort of scraping the barrel a bit. Kuiper Cliff Super Earth from 2003, the Kuiper Belt, which is the asteroid belt in the outer solar system, suddenly drops off, and the Kuiper Belt may have a super Earth-sized object out there at around 50 astronomical units. Like Mike Brown uses Perturba as a sort of a naming of Planet Nine, but things like George and stuff like that has been sort of given for Planet Nine. Persephone, the wife of Pluto, a petition on change.org said they should name the planet David Bowie, when any potential moons to be Ziggy Stardust or Starman. And but reason why we haven't discovered it yet, it's not enough orbital data. But it's kind of almost like Vulcan has now moved away from the center of the sun, not the center of the sun, being between Mercury and the sun, to be way out in the solar system. Is there something else out there? There's various sort of things we've got these days as modern computers and modern telescopes and stuff, which suggest that maybe we can do some model. There are sort of computer models of the solar system which could sort of help with this situation. And one of them is it's not the nice 5-planet model. It's actually Nice, as in the French city. And there's actually 6 biscuits there, not 5. Suggests that the 5-planet model is there was 5 giant planets originally in the solar system, and one of them got thrown out by sort of various effects and became a rogue planet. And so we sort of see the effects on those Sednoise orbits from a sort of a 5th planet there. Also associated that was the Grand Tack, where Jupiter acts like a sort of a boat and sort of like sort of tacks on into the solar system, disturbing things on its way, but here it gets pulled back by Saturn, and sort of the Grand Tack could sort of have thrown this 5th large planet out of the solar system, and also it sort of could have disturbed the formation of Mars enough for it to sort of be quite smaller than Earth and Venus and stuff like that. So maybe there was a 5th planet. Maybe we're seeing the relics of a 5th planet or Nemesis or something along those lines. Maybe those orbits are, when the 5th planet, the 5th giant planet, I should say, the 5th giant planet got thrown out of the solar system, and therefore that's why all those Sedna objects and various things are all on one side of the solar system. One of the other things is jumping Jupiter effect, which I think that somebody, that was such a great word, jumping Jupiter, such a great phrase, that I think that this guy probably should have said that in that film, but I don't think he did. That's Emmett Brown from Back to the Future. That Jupiter was actually just jumping around the solar system, and it's sort of like, well, not jumping Jupiter itself. The 5th planet jumps around the solar system and perturbs Jupiter's orbit and sort of makes Jupiter move a bit closer and Saturn a bit further away. And if you don't have a Saturn-sized object, eventually you'd have a hot Jupiter like we see around sort of various stars of Kepler. I quite like that photo because it actually looks like Brian Cox on a skateboard there, jumping over Jupiter and stuff like that. So the legacy of Planet 9 now, that maybe we're seeing the relics of those objects there. Maybe Planet 9 did exist. Maybe there was another planet in the solar system that got thrown out by various gravitational interactions in this really sort of dynamic system and dynamic world that we sort of live in, with all these sort of gravitational anomalies and sort of all interacting together. Maybe Planet 9 got thrown out. But as Chris Lintott, you either sort of choose to believe in Planet 9 and planets like Vulcan and stuff like that. You can choose to believe in either or. You can make the maths explain whichever you want. And Planet 9 may have existed in our solar system, but is now gone rogue. And there we are. That's the end of my talk.
Thank you very much, Andy. Cheers.
Hopefully you saw that, because all I saw was my screen.
Yeah, now we saw everything. Yeah, it's fine. It went really well. Yeah, it was a good story of like how science happens, wasn't it? It was really a sort of long journey of discovery. Yeah, so if anyone's got any questions, just chip in straight away. You can type them in the chat if you want.
Yeah, just curious why Lintot is so keen that it does exist.
I think sort of he's a sort of obviously a proponent of the maths. You know, professor of cosmology. He looks at the maths and all these sort of these models and stuff, and he sort of really thinks that Planet Nine exists somewhere out there. I mean, they've nailed it down to be somewhere near Orion for the next 1,000 years, which is a bit unusual because it's that'll obviously have to have an inclined orbit to be there. But nobody's found it. I mean, if you think of all the stuff that's been up in space, telescopes, satellites, all sort of like, you know, crazy, like, you know, we've got massive telescopes here and we've seen diddly squat of Planet Nine at all. A big planet out there leads me to suggest that maybe it's more of a rogue planet that disappeared. And yeah, sort of from the solar system.
Yeah. Interesting.
So the thing with the NICE model, the NICE model, is it also sort of like sort of corresponds with sort of formation of the asteroid belt and late heavy bombardment and various things like that. So the fifth planet hypothesis, or the fifth giant planet hypothesis from the NICE model, has got like a much higher probability of being that Planet Nine, which is escaped. I think it's 10 times more likely, rather than a Planet Nine that still exists.
Okay.
Yeah, well, this reminds me a bit of like Lowell's Mars canals as well. Like, there's been so many of those. We've got a good question coming through here from Nathan. What role did you think of the obscure orbit of Mercury had to play in Einstein's pursuits, or was it just a side?
I think when sort of Einstein was more about thought experiments, so he was one to just sort of sit there. I mean, he obviously did his job as a patent clerk, but he was sort of more a guy to sort of sit there and think about these sort of people in boxes, people falling off roofs, lightning strikes and train platforms, and all these things. And he would then take the mathematics and try and sort of like, you know, convince himself using mathematics. So I think when he came up with the general theory of relativity, he knew he probably could resolve the Mercury situation there, but he didn't really set out to tackle Vulcan itself. It was sort of kind of a happy coincidence at the time, and it was a good one because obviously, yeah, I think he was aware in Vulcan. Nathan, he probably knew of it as an object, but he never really sort of went out there to sort of work on Mercury. But fortunately, there was so much data by that time that, you know, with that amount of information, to be the first test of general relativity that he did, and that was the one that worked. And then people went to sort of observe solar eclipse. So really, the sort of the destruction of Vulcan by Einstein is actually the first step in a big long path of proving general relativity. But he didn't set out, as far as I am aware, to sort of tackle the Vulcan and the Mercury problem there.
Yeah, cool. Yeah, I reckon Wikipedia does need correcting. I think you're onto something there.
Yeah. Well, one of the source materials on that Wikipedia was lots of letters written in French, which I don't understand. So correspondences from Urbain Le Verrier to people like John Adams and sort of other people like that. But I do think that maybe it's wrong, and I'm not. Yeah, I think you need to get in there and resolve that and put iota aquarii rather than pi aquarii in there. So.
It's quite easy to edit, though. I've edited.
I was so surprised, honestly, to see such a massive discovery of a planet was written up wrong. I mean, come on, this is like, you know, people say Wikipedia is full of nonsense and stuff, but you know, that's such a massive discovery in science that they've got it wrong. It's crazy.
What was the estimate for the size or the mass of Planet Nine? Is anybody kind of done the calculations?
Six plus Earth mass.
Six
plus. Yeah, generally that's from Mike Brown from Caltech. The Kuiper Cliff super Earth is probably Earth size, if not slightly larger, twice the size of Earth. These are almost like the variables that Urbain Le Verrier was mucking around with. You know, when he was just throwing numbers like about the size of the planet, the mass of the planet, say, oh yeah, we'll chuck these variables in and see if it works and stuff. So you know, nobody really knows. But you know, I personally thought with all the satellites and stuff we've had up there looking at the sky and various things, we'd have seen something by now. But Chris Lintott seems to think it's still out there waiting to be discovered.
Yeah, I guess we're on a better footing mathematically than we were with Newton's equations alone. General relativity has been pretty well tested now.
But that makes me sort of think that it should have been definitely discovered then.
Yeah.
Yeah, great talk. Hey? Yeah.
Thank you. Yeah, a talk about something that doesn't exist in astronomy.
A lot of research. A lot of research on something that doesn't exist.
Something that's not there at all that nobody can see.
Negative results are just as important as positive ones.
Research.
Fake news which heats astronomy. Yeah. Let's dedicate that to Donald Trump, shall I?
Yeah.
Existence.
Anyway.
Right. Thank you very much, everybody.
Any other questions then?
Thanks a lot, Andrew.
Thank you. Cheers.
Yes.
Thanks, Andy. Great talk.
Yeah, if you just joined us.